This conference will now be recorded.
Good morning, Sudipto.
Good morning, sir.
Is my voice clear?
Yeah, your voice is clear.
Shall we start or we'll wait for 5 more minutes?
Okay, we shall wait for 5 more minutes for
Okay.
participants to join.
Yeah,
So we'll start from 10:05. Okay, sir.
10-5. Okay,
Yeah.
sharp. Shall I start, Sudipto?
Yes, sir. You may start, sir.
Yeah. Good morning, one and all. So, welcome to the second day of today's FDP. So, today Sudipto will be taking care of today's total session. He will be covering about converter and machine toolbox. So, basic level, real-time simulation he will be covering. So everybody have got the this license is being activated. So please, somebody is with smartphone. We can't help, like you need to use laptop so that practice is good. So please do practice. Otherwise, things will be left here only. So practice more. That would be very important. So as Sudipto's like introduction is done, then what kind of things we need to connect, and that slowly he will explain. So try to practice the things. Otherwise, things you will forget after some time. So my sincere advice is, like load down with that Typhoon HIL software, and license is activated, and uh, you know happy learning for everybody. So happy Sri Krishna Janmashtami to everybody. So I will hand over the session to Sudipto.
Yes, sir. Thank you for the introduction part. So I should take over the session. Good morning, everyone, and welcome you all to the second day session of this FDP program. My name is Sudipto Poddar, and I am working as a marketing and support engineer at Co-ops Typhoon HIL India. So basically, I hope you everyone have got the license key which I have sent, and it is being activated from your side. So today we are going to give the introduction part, how to work in the software, what are the tools available, what are the library components we had got, and how it is different from the conventional software you are using at present right now. Okay, and also some extra tools which Typhoon offers, and how it is easy to work in Typhoon rather than other simulation software. Or I would say one thing, that the Typhoon is not only a simulation software; it is a real-time simulation software, and you can also perform real-time simulation as well as controller hardware in loop simulation and power hardware in loop simulation. Also, rapid control prototyping. So today you can see that how you can interface the actual signals in Typhoon HIL, how to take out the signals from Typhoon HIL simulator, and what are the steps if you're performing only simulation alone, and what are the steps you need to do when you're performing real-time simulation. So all this we are going to discuss in this 2 hour sessions, and also we are going to develop a basic model of our single phase inverter, and we are going to demonstrate some example models like mppt boost charger model, and as well as grid kinetic converter with pq control. So with and I would suggest that please turn off your mic. Okay, so basically we are going to develop the modeling, as well as we are going to demonstrate some example models along with the SCADA panel, because SCADA panel is completely new to you. Those who have worked in Typhoon, it's okay for them, they know it very well, but those who are new to this platform, it is going to take much time to get acquainted with how to work. So, sorry for the interruption. I think someone has turned on their mic. That's why. So I just want to know, is my voice clear, audible, or there is some disturbance in it? Am I audible to everyone? You can share your views on the chat box.
Sir. Yes, sir. Yes, sir. It
Okay,
is audible.
okay. Thank you for this. And where was I? Okay, so yeah, one thing I'd like to add, that if anyone faces any kind of issues while I'm demonstrating, so they can mute unmute themselves and they can speak and they can ask their queries. Also, you can write your queries in the chat box, so we'll be happy to help. Okay. So one thing I would just like to add that those who are new to this platform, SCADA part configuring the signals, it is going to get difficult, but whenever you do the practice part, you will get acquainted with it. So better you just watch the videos first, which I am demonstrating. Later on, go with the recordings. So we'll provide the recording link for the GoToWebinar. Okay. To your WhatsApp group, and Venu Madasar will provide to you and rest Anurag team, Professor Dinesh, Professor Yasin, and Professor Vasu, as well as HOD Mr. Anil Kumar. I'm thankful to them. So let's start today's session first of all. So basically, yesterday we have demonstrated some introduction part for Typhoon HIL, how we have what are the processors we have got, like we are based on FPGA, and we have two CPU processor for signal processing part. Okay, so first of all, I will just show you some images for Typhoon HIL 402, which I had clicked from my camera. So let's just stop. Okay. So I think my screen is visible to everyone. Okay. So this is the image of Typhoon HIL 402. Okay, so it is a smaller in size, much smaller in size than a laptop. Okay, and much lighter in weight. And over here you can see these are the analog I/O pins, analog input and output pins, and these are the digital input and output pins over here. Here 16 analog input pins, 16 analog output pins are available with ground, as well as here 32 digital input and 32 digital outputs are present. So remember, 402 configuration have 16 analog input pins, 16 analog output pins, and 32 digital input pins, 32 digital output pins over here. These are, you can see, digital I/O. This is the indicator button. When you turn on the simulator, it will glow, and when you run the simulation, it will blink. Okay. So now we'll move forward to the next image. This is the backward side view of this Typhoon HIL 402 simulator. This is the basic one from Typhoon HIL, and this is the cable, USB cable, which is going to connect with your laptop. So you can perform, you can connect the software and you can run the simulation in the Typhoon HIL simulator. So this cable is going to connect with your laptop. This is USB cable, and this is the power cord over here, standard power cord for providing the power input to the simulator. These are the two fans over here, and this is the turn on and off switch for the simulator. Okay. And this is for Ethernet connection. So this is the backside view of this Typhoon 402. Next over here, if you see, you can see these are the analog I/O pins over here. It's written 1 to 32. You can see, and over here it's written A, B, C. Okay, so how to configure it we'll discuss when we open the software. So over here you can see it is written 1 to 32 pins and A, B, and C. So whatever this A denotes and B denotes and 1 to 32 means, we're going to discuss this part. Similarly, in digital IOs, we have this 1 to 32 and ABC. So I just go back to my software and open the documentation part and make you show that what this part means. So this is the Typhoon HIL Control Center. So I just go to this documentation hub over here, and I will just open this HIL46 hardware user guide. So just give a double click onto this part. So it will open. So now you can see a PDF file is opened like this. I just scroll it down. Just a moment.
Hindi ko na
I'll just slide it down and I just click the HIL 4 series, HIL 402. You can see the processor configuration, number of analog input outputs and digital input outputs, as well as compatibility. I'll just move to the pin configuration over here and just scroll it down this page. Okay, so here you can see HIL 402 and HIL 404 IO pin out. So here you can see row A, row B, and row C. So on row A, you can see pin number 1 is analog output 1, and it continues to over pin number 16, which is analog output 16. After that, plus 12 volt output you will get from the simulator if you connect to the pin number 17, and minus 12 volt on pin number 19 and 20. Similarly, plus 5 volt on 21, 22, and if you want to provide analog input signal inside your simulation, you need to provide a signal from pin number 25. So pin number 25 is your analog input 1, written as AI1. Okay, so these are all these analog input pins, which starts from 25, pin number 25 to over here, row B, again from pin number 25 to pin number 32. So this is like this. Similarly, on row C, all these are ground pins. Okay. And for digital, you can see on row A, it is digital input 1 to 32 on row A, and digital output on row B, 1 to 32. So if you go back to the image, so you can see 1 to 32. That means for analog series, if you come back again, for row A, 1 to 16 number pins is for analog output. So that means from over here, if you start counting, 1 to 16 number pins is for analog outputs. Okay, and for analog input pins, 25 to 32, and the row B also 25 to 32. Means this side is for analog inputs. Okay, so these are the analog input pins and these are the analog output pins. Similarly, we need to configure for digital IOs channel also. Okay, so like this we can configure the pin outputs if you want to provide signals inside the simulation, or if you want to take out some signals from simulation to the outside world, or the PWM channels if you want. So like this you can use it. Okay, so I just minimize it. Go back to the software. So if you double click on the Typhoon icon on your desktop, so you will open this Typhoon control center. Okay, so over here you can see it is written as hardware info. So if you click on it, you can see it is showing unable to detect any HIL device. That means right now I am not connected to any hardware in-loop simulator to my software or to my PC. That's why it is showing this unable to detect any HIL device. That means we can perform only simulation while using the software. So if you want to do real-time simulation and nature simulation, you need to connect with the hardware, and you need to check over here whether your device is connected or not. Whenever your device is connected, you will get all the details of the device over here, connected device over here, with the configuration itself. Okay, as well as the firmware release date and the HIL device ID. All the details of the device will get. And one thing I would like to say, Typhoon HIL provides upgrades every quarter of the year. Okay, so if you want to upgrade your software, whenever upgrade comes, green arrow will appear over here. So if you click on it, and it will show to download the software. So it's preferable first uninstall the previous version and then install the newer version which is available. So right now this is the latest version, version 2020.2. Okay, so next it will come 2020.3. So after means after September it will come. Okay, so this is for online help. If you require any online help materials, you can click on over to this. Else, for offline help or documentation for the software, how to work it, or work on it, how to install the software, everything will be available over in this documentation hub. Also, some details regarding Typhoon HIL application examples models is provided in this documentation hub. I'll just stop with it. You can see over here Typhoon HIL Quick Start, Typhoon Software Manual, Typhoon schematic editor library means all the library components which are available in Typhoon software, how it is developed, and what are the principles behind it is defined over in this document, which is Typhoon schematic editor library. Similarly, regarding whatever this configuration or hardware series, if you have or if you are willing to purchase, so you can go to this HIL 46 hardware series user guide, and you can find the details for the real-time simulator products from Typhoon HIL, and also the pin configuration which I have shown to you. Okay. Similarly, if you want to use any Texas Instrument cards like F2835 or F2808, similar type of Texas Instrument card, as a controller, so how to configure it and how to connect with our real-time simulator and do controller hardware in loop simulation. So all the details regarding that part is provided inside this document. Similarly, if you want to use a multiple HIL device, so details regarding that, how to use, how to connect multiple HIL device in parallel is provided over here. Okay. Also, if you are using multiple Texas Instrument card for microgrid simulation or microgrid controller hardware loop simulation, you will get the details from this microgrid DSP interface user guide. Similarly, for this DSP interface user guide, you will get these details, and these are all the configurations or details regarding our interfaces like Launchpad interface. Okay. And here are some technical notes for analog output configurations, battery modeling, and application. You can model your battery. All this part we're going to discuss, that how you can model your battery and how you can do for PV modeling part, also for conductor and circuit breaker modeling and thermal modeling of power electronic devices. So if anyone is working on this area for thermal modeling of power electronic devices, you should go first with this document, and also some example models are available inside Typhoon HIL software. You can go through that also. And yes, and the next one is Typhoon HIL application library. If you double click on it, let it get open. So over here you can see various examples regarding the example models available in Typhoon software. About that documentation part is available over here, like grid current converters, automotive, like electric vehicle, aerospace, how to guides, communication protocols, marine power supplies, power systems, as well as power quality and macro. So whatever the example models available in Typhoon software, regarding that, how it is done, how the controller part is being developed, and what are the fundamental principles behind that model, all this being discussed inside this documentation part over here in Typhoon HIL applications library. Okay. So after that, we'll move to this API documentation. If anyone is willing to test their model or do the simulation using scripts by writing scripts, so I'll just tell you that Typhoon HIL is based on Python. Basically, Typhoon HIL is primarily based on Python software, and Python is an open source. So that's why we provide API over here. So you can write the scripts, you can perform the simulation, you can record the data just by writing scripts using this API. So for this, regarding everything is provided over here, API, SCADA API, Typhoon testing. So we'll discuss that part whenever we come in details. So these are all the documentation hub, and whatever the things provided inside the software are already available over here in the documentation hub. You need to explore it first, so you'll get all the details regarding this and how to work on it. Next is license part. If you click on it, you can see the details of the license and of the scripts. Okay. Now, if you click on this logo for Typhoon HIL, it will directly redirect you to the Typhoon HIL website, and this is the version which I've talked about. And if you want to see what is new to this version, you just need to click over here, version 20.2, and you can see what is the new updates which came with this version. Okay. Now, over here, you can see all these tools. Actually, when you open the software, it will look like this, just like this. Schematic editor, SCADA, Typhoon test ID, test suite. If you click on the selection tools, it will open like this. Okay. So basically, in every simulation software or every real-time environment, first see, basically we do not get any schematic editor or simulation part in real-time environment. So we get in a simulation software. So we'll talk about a simulation software. So in every simulation software, you get a place where you can model your simulation, where you can monitor the simulation. Means you can check the results, you can capture the plots, you can capture the graphs. Okay, and next is the place where you write the scripts. Okay, so these three tools you get in simulation software, which you have used at present in every environment. So what extra you get in Typhoon HIL? You will get a waveform generator tool in Typhoon HIL. Waveform generator is a tool where you can generate your PV graphs as well as you can generate your own source file. Means you can generate your own voltage and current source. You can provide spikes onto that source file, and you can use that source file inside the schematic editor while you are running simulation. Okay. So all this part you can do in the waveform generator. I'll discuss. I'll come to that part. That how we can create your PV, how we can see the PV curve, and how you need to provide the parameters, and how you can also generate your own source file. Okay. So, and the next thing is that you are getting script editor. Script editor is based on Python. So I think yesterday you have seen how to work on script editor. Is if you open script editor, you will get three options. Either you can use your own system Python, or you can use Python embedded with Typhoon. You can write the codes. Similarly, we have got Typhoon Test IDE platform, integrated development environment, is a tool which is used to run Python test and display the results and log of each test using Typhoon API library. Okay, so whatever you are doing, you are modeling in schematic editor and HIL SCADA, you can perform using Typhoon Test IDE. Okay, by writing codes. And the next thing is test suite demo. So this test suite is being designed by Austrian Institute of Technology, and this tool is used for pre-certification purpose. Okay, so what is pre-certification? I'll just give you an example that if a solar inverter company develops a new type of controller for their inverter, okay, or the converter, they develop a new type of controller and they want to sell that in the market. So what they will do, they will first go to a certification agency and they will test that controller with the setup and for and test in certain various conditions, and they will get the certificate. And after that, they will get the certificate. They will go to the market and they'll sell that product. These are the steps. If you develop a new type of control, okay, that that certification agency provide the certificate that this controller passed through various tests like this is this and etc. So these are the steps need to perform. So what this tool offers, let's take an example. If you go to the you develop the controller, you go to the certification agency, and your controller fails in first attempt. Okay, so you need to first create the certification agency for the tests, and then you need to go back again. You need to make the readjustments, and then you need to come back to the again to the certification agency, and you need to test. For that, you need to pay once again. So it's okay for one time, 2 time, but if you fail continuously, then how you are going to test your controller? So for that purpose, what we have done, we have provided this tool where you can go for the pre-certification. Means you can test your controller for various conditions like VDEW, AGTR3, low voltage right through, high voltage right through, low frequency right through, high frequency right through, as well as UL1741 conditions, and MPPT static and dynamic efficiency tests. Okay, so you can perform all the tests and you can generate your test report, and then you can be assured that okay, my controller has passed all the tests, and now I can go to the certification agency and I can certify my controller. Okay, so this is the benefit for this test suite. And next is signal analyzer, where you can analyze the signals which we have captured from HIL SCADA over here. Whatever the signals we have captured from this HIL SCADA, you can analyze in signal analyzer tool. And next is firmware manager. Whenever a new update for the software comes, you need to go to this firmware manager to update the firmware for your hardware. Okay. And the next is testing calibration. If you want to calibrate your analog IO pins, If there's any issue, then you can use this tool to test and calibrate that IO pins. Okay. Next, this two important tool is schematic editor and HIL SCADA. This is the place where you just develop your model, and there are library components available. You can generate your create your model, and after that you need to compile, and this model is going to get offered on this SCADA platform. Over here, various widgets will be available. Okay, so you need to drag and drop these widgets according to your applications, and you can perform the simulation. Here, SCADA means supervisor control and data acquisitions. Over here, we are just monitoring our model which we have developed. We are monitoring the results as well as we are data logging it, and we can also change the simulation parameters while running simulation over here in HIL SCADA. So we are going to see all this part. So first of all, we'll just open the schematic editor, and you can see we're just running the simulation only. So we'll first open the schematic editor at first. So I just click on schematic editor. We'll give it some time to open. It will take a little bit of time. Okay, so here is our schematic editor. If you open the schematic editor, it will look like this. If you open any recent schematic files, it will be available over here. And over here, you can see file, edit, view, model, Windows help. And there are some tool icons over here. Like if you want to create new schematic, you can click on to this, open a model, save as, etc., print, etc. And similarly, undo, redo, cut, copy, and zoom in, zoom out, and rotate 90 degree, clockwise and anti-clockwise, flip, horizontal flip, vertical flip, and this is model initialization script, and this is compile schematic, and this is compile schematic and open model in SCADA. We are going to use this part frequently, not this button. But whenever we have created our model, we are going to click on this compile and open model in this SCADA. Okay, so now in file, if you click on file, you can get the options for new. And if you want to create a new model, you can go to this new model. And if you want to create your own library, so you can click on this new library, and a blank page will open, and you can drag and drop components, or you can write a code for this new library option. Okay. Similarly, if you want to open any model, existing model, you need to click on this open model. Or if you want to open the library, you need to click on this. Similarly, if you want to open any example model, you need to go to this open example model sections. So similarly, save as, export library, close diagram, and etc. Similarly, if you have developed any model in PC, then you can use this import PC schematic option to call back that model into Typhoon environment. Means PC software is directly compatible with Typhoon HIL. So if you have developed any PC schematic, you can use this option to take back that model inside Typhoon simulation for real-time purpose. Okay, and then export to PDF, export to image, etc. If you want to export your model into image format, then you need to click onto this. Similarly, you have this edit, view options, model, Windows, and help over here. So first of all, I just click on this new schematic. You can click over here, create new schematic, or you can go to this file, then click on new, and then click on new model. So whenever you click onto this, it will appear like this. Like it will ask for the hardware product, hardware configuration ID, simulation method, as well as simulation time step. Okay. So over here you can see it's written HIL 402. So if your model is compatible with HIL 402, or if your model is basic, so you can go with this HIL 402. Also, if you do not know all about this, You can also go with this HIL 402 rest. If you know the complexity of the models and how to work on it, you can just click over here and you can select the device as per your choice and you can develop your model. Okay. So first of all, I'll go to with HIL 402 and next is asking for configuration, hardware configuration ID. If you want to know more about this hardware configuration ID, then you need to click on this device table, and after clicking on this device table, it will open like this. So over in this device configuration table, you can see there are 6 configurations for 402 device. Number of SPC. SPC means number of standard processing cores, as we have discussed in previous day that 402 device have 4 core of FPGA primarily. So over here you can see number of SPC on configuration 1 is 3, on configuration 2 is 4, and configuration 3 is 2. Similarly for configuration 4 is 2, and 5 2, and 6 2. Okay, respectively. And the number of machine solvers over here is 1 0 0 1 2 1. If you want to use 2 machines, then you need to go with configuration 5. Okay. Similarly, number of signal generators, lookup tables, PWM channels, as well as number of contactors for SPC, and is available details are available over here. Let's take an example. If someone someone want to work on converter power loss or thermal modeling of power electronic device, then you need to select this configuration 4. In configuration 4 will allow them to work on this thermal modeling of power electronic device. Okay. So this is how you can select configuration, and if you want to see more about the other device details, so you need to click on HIL 602. Like I have opened this device table. Similarly, you click on HIL 604, you can see all these details over here. Okay, so now I have discussed regarding hardware configuration. If you do not know much about this, go with the default. Then simulation method. Over here, you can, if you click on this, you can see 4 types of simulation method: exact, trapezoidal, Euler, and bilinear. So if you know, it's good. If you do not know, you can go with the default itself. So I'll go with the exact method and the simulation time step. Over in Typhoon HIL, there are 2 time steps which we need to provide. One is for the planned part and one for the controller part. Okay, means one for the plant or the converter or the machines or the voltage source we are using, or and the another one time step we need to provide for the signal processing components. Okay, so we are selecting the simulation time step for the planned part over here. Okay, so if you know the time step for the planned part, you can select from 500 nanosecond to 20 microsecond over here. Else you can go with the auto. So if you click on auto, it will select the best time step suitable for your model and it will execute. Okay. So this time step is for your plant model because we are running the plant part in FPGA and we are running the controller part in CPU processor. Okay, in our Typhoon HIL simulator. So whatever the time step we are selecting over here, it's for the plant part. So we'll click on next, then it will ask us to review what are the settings we have taken, and then we'll click on finish. It will take some time to load the library, so we'll wait for that part. First time when you're opening the software, when you're opening this new schematic, it will take a little bit of time. Okay, so you can see a blank page will open over here. It's written new schematic with current date and time, and over here you can see library explorer. So these are all the Typhoon library. If you cannot see this library section, you need to go to this view and show and hide docs, and you need to click over here. Okay, so if you cannot see this library explorer over here, that means it is disabled on this part. So you need to go to the view section and then go to show hide docs, and you need to enable this library explorer part. Okay. So these are all our library from Typhoon HIL, which is based on electrical engineering domain. Someone has turned on the mic. Please mute yourself. So over here you can see circuit breakers, double pole MOE circuit breaker, or double pole MP circuit breaker, single pole MOE circuit breaker, as well as triple pole MOE and MP circuit breaker. So this is MOE circuit breaker, which is being designed in the model based of ABB stored energy motor operated circuit breaker. Over here you can see here are the control options: control length, close, delay. Also you can take output over here. If you want to provide signals for this MOE control circuit, so you need to provide onto the pin, and if you want to take out the outputs, so you can use this port over here. And if you need any more details regarding this circuit breaker, so you need to go to this help options, and it will redirect you to this documentation part for the circuit breaker. So whatever the library we have got in Typhoon HIL, we get these help options and all the details available regarding that specific library component will be available. So here you can see motor operated circuit breakers from ABB, and if you scroll down a bit, you can see details for this contactor. Okay. So like this, we get all the details for every components available in Typhoon software. So now this is a master pack circuit breaker from Saturday. So if you double click on it, you can see the details. It is based on the model of Saturday master pack series circuit breakers. Okay. So similarly, help options is available over here. If you want to see more details regarding this circuit breaker, you can go through it. Sorry. Similarly, for I just remove this part. Okay. And similarly, we have this communication library over here. If you click on it, you have C37118 protocol. Those who are working PMU, you can use communication protocol to connect actual PMU. Also, you can model virtual PMU over here in Typhoon software. Example models are provided for that. Similarly, we have this CAN protocol for communication or cyber security. Those who are working on cyber security purpose, you can use this communication protocol to connect with actual hardwares. Also, you have CAN protocol, TNP3, distributed network protocol 3, Ethernet variable exchange, I61850. Those who are working with relays, you can use this communication protocol IEC61850 to connect with actual relays, and you can control that. Similarly, we have this Modbus, and if you want to control any SCADA, actual SCADA, you can use this OPC platform to connect that, and you have this serial communication protocol. So all these communication protocols which are required is available inside this communication library. Similarly, we have this contactors. Over contactors, you can see double pole double through contactors, double pole single through contactors, multiple single through contactors. Similarly, various contactors are available over here. These are ideal, these are non-ideal. You can see it is a green color. So if you want to use this part, you need to go to this model and schematic settings. You need to change this configuration ID. Like for non-ideal switches, you need to select, you need to go to device ideal, device table. Over device table, you can see in this part, non-ideal switches is available on configuration 3. So if you select configuration 3, then it will get activated over here. Okay. Similarly, we have this converters libraries already inbuilt, like those are working with MMC, thermal network already provided. Similarly, we have got AC switch, active full wave rectifier, buck boost VNR rectifier, 5-level flying capacitor inverter lake, flyback, AD converter, 8-6 single phase inverter, MMC lake, single level flying capacitor inverter lake, single phase diode rectifier, and various you can explore through this library. So these are all the converter sections, and I will demonstrate that how to work with it, and by demonstrating single phase inverter, how to give control logic to this inverter part. Okay. Next is machines. You have got machines from 6 phase to 9 phase induction machine with squirrel cage. Also, brushless DC machine is available. DC machine is separate, and parallel acceleration double bed induction machine, and induction machine with squirrel cage also. Similarly, permanent magnet motor with silent rotor, cylindrical rotor, etc. Single phase induction machine also. So if I drag and drop a machine over here, you can see the parameters over here. You need to provide electrical parameters, mechanical parameters, load. The most important part is load. Over here, you can see the load source is referred as SCADA or external. If I select this option SCADA or external, that means if I select SCADA part, means I can provide the load part of this, like we have selected load type as torque, so I can provide the load to this machine from SCADA, HIL SCADA directly. Okay. Else, if you want to provide the load for this machine from outside this simulation part, you need to click onto this model and you can design. Click on OK, and you can provide the torque over here directly. Okay, so I'll just open it. For feedback, you can use this encoder protocol like ENDAD, PISSSI, and similarly, you can take out outputs also. So I'll just click this part. And let's take an example. We have done motor modeling of a new type of motor in JMax software. So you can directly call that using this option, powered by motor synchronous machine JMax. Also, JMax is directly compatible with Typhoon HIL. So you can call the machine models developed in JMax software directly into Typhoon itself. Okay. So I'll just minimize this one. Similarly, we have this measurement block, current measurement, current RMS, voltage measurement, and voltage RMS. And in MapRead, we have already predefined models for back-to-back converter, diesel genset, energy storage, infrastructure, power plant, wind power plant. So if you drag and drop diesel genset, so in legacy, there are two types of diesel genset model available, like conventional type and the user interface type. So if you drag and drop this diesel genset over here, okay, so if you double click on it, you can see the details for this diesel genset, and you need to provide only parameters like nominal power, phase voltage, etc., synchronous machine parameters, etc., and governor engine parameters, exciter parameters, and PI parameters. Okay. So you need to just provide the parameters if you know. Else, if you want to change the see the what is inside this diesel genset component, we need to right click over it and click on mask and go to look under mask. So if you click on this look under mask, you can see this generator model, diesel genset model over here, that how it is developed. And if you want to change anything inside this controller block, so first of all, you need to go to this root. You need to unlink it. First, right click on it, unlink this component from library. Then you can make the changes. So then you can go to the mask, look under mask, and go to control, and you can see all the control logic. If you want to make any changes inside it, you can do it right now, like this. So already inbuilt MapRead library is available. Those who want to use with conventional part, they can just drag and drop, provide the parameters, and they can go work with it directly without wasting any time. Okay. Similarly, we have grid loads, loads like constant impedance load, variable load, okay, meters, as well as protection relays like under voltage, directional power, low power, instantaneous overcurrent, etc. All these are available. Also, example models are available for it. So I'll just show it later. Next, passive components like capacitor, inductor, etc. Also, variable capacitor, inductor, resistor is open. Okay, I got a question from Kuda Ranjit Kumar that when we open the software and going to open a new model, it's saying that schematic data is not responding. I think you just refresh once back, and I think that you have opened multiple times Typhoon HIL software. Okay, so open it once and then open the schematic editor. Okay. Else, if you face any problem, you can contact us. So after this passive component, then we have this ports. For when you design any subsystem model, then we require this ports. And then in signal processing, we have this discrete, like a delay, differentiator, discrete state space, as well as rate limiter, transport delay, unit delay, etc. for designing your controller part. Similarly, in extras, you have got FMU import. This is required when if you have developed any model in Simulink, any controller model in Simulink, and you want to use that controller in the Typhoon HIL, you can use this option FMU import, and you can call directly that controller over here using this FMU import. Similarly, we have this PID controller, PWM modulator, RMS value, and ABC to TQ, ABC, alpha beta to ABC, and TQ to ABC, and TQ to alpha beta. So, what is the beauty of our software is that if you drag and drop the PID controller, and if you double click on it, you can see here you can provide the values for KP, KI, KD, and you can go if you know the values. If you want to go for trial method, then you need to hit and trial method, then you need to select this KP source as external and then click on OK. If you select this KP source external, a pin will be available over here. And if you use a SCADA input, like if I use a SCADA input over here and connect with it, so whatever the values I provide from this SCADA directly while running simulation, I can change this KP values online. Okay. So these are the steps how we can use a hit and trial method inside this PID controller. Okay, like this. Similarly, I'll go back again to the library sections and signal processing, and then function tables. There is 1D lookup table, 2D, 3D lookup table, also advanced C function block, and C function block. Okay. So if you want to write C codes inside the Typhoon model, or you want to develop any controller using writing C codes, so you can use this C functions. Also, you can call C codes from other software like MATLAB Simulink or PC, and you can use that C codes over using this advanced C function block. Also, you can call DLL files from other software, generating from other software, and you can use it in Typhoon using this advanced C function block. Okay. Then comes this logical operations and math operations, similar which you have used. And for power measurement, you have this harmonic analyzer, phase difference, positive, negative, zero power meter, single phase phasor, PSD measurement, and phase measure. All are available over here. Similarly, governor model, exciter models, steam turbine models are available. For sources, signal processing sources like analog input. The difference is here is that to double drag and drop this analog input, digital input, etc. Also, there are sinusoidal source, square wave source, step, and triangular wave source are available. So, if you want to provide any analog signals inside this schematic, okay. So let's take an example. If you want to take any PV voltage inside the schematic and you need to design a model, so you need to take and drag and drop this analog input pin, okay, and you need to select the pin number as like we have selected 402, and you know that 402 has 16 analog inputs. So here you can see the pin number 1 to 16. So in which pins you are providing signals, you need to select over here. Like if I select 7, then I need to provide the signal on input pin number of 7, means analog I7, AI7. Okay, and you need to provide the execution rate over here, and then you are ready to go. You can take the signal. Similarly, if you want to take any digital input signals inside the schematic, you need to select this pin number, as I have discussed that 402 have 32 digital input pins. So you need to select from this the input pin, and then the type, and then execution rate, and then you can use that digital input signal inside the schematic model. Okay. So I just delete this part. Then I'll go to the sources. Over here you can see battery. Let's drag and drop it. Current control current source, externally controlled current source, external control voltage source, fuel cell, photovoltaic panel, as well as signal control current source, signal control voltage source, three-phase constant power load, single-phase constant power load, voltage control current source, voltage source, all are available over here. So I just discuss regarding battery first. So if you double click on battery, you can see this option. And if you want, you can select the battery type like lead acid, lithium ion, nickel cadmium, nickel metal hydride, and user defined. If you want to go for your own battery modeling part, you can select this user defined. You can provide the parameter, terminal voltage, capacity, initial SOC, full charge voltage, etc. You can provide all the parameters and you can click on this preview SOC curve. So if you click on this, you can see the SOC curve of this battery part. Similarly, for single person, you can take SOC charge output. If you click on this, you will get a port over here for taking this SOC charge output for signal processing part or for controller part. Okay. So if you click on OK, like this, you can design your own battery, or you can use a battery models available over here like lead acid, lithium ion, etc. So I'll just remove this part. Now I'll come to this part, which is externally controlled current source. Means if you want to provide any current source from outside world inside the simulation, then you can use this externally controlled current source and select the input analog input pins, just like I have defined for the analog input pins. You can use that also, or you can use this part also, external current source. You need to select this pin number and then you need to click on OK. Then you are ready to go. Similarly, you have this externally controlled voltage source for providing any voltage from outside. Okay. So I will select this part. This is current control current source. And next is fuel cells. If you double click on it, it's based on proton exchange membrane fuel cell type, and you can provide the parameters like electrochemical characteristics, purity coefficient, fuel cell geometry, operating conditions, polarization curve, stack, and thermal coefficients, etc. You can provide all the parameters which are required. And if you need any help, you can click onto this help button. The documentation for this fuel cell will open. Okay. So I'll just click on OK and remove this fuel cell. Next is photovoltaic panel. Over inside this photovoltaic panel, if you double click on it, you can see that there is no option for providing irradiation and temperature. Okay, so you can provide that irradiation and temperature from SCADA. You need to provide there, and also the type of photovoltaic panel. Okay, so I'll just close this one. Similarly, in test suite, you have this DC meter, anti-aliasing, dynamic grid fault, and simulator. And in transformers, you have ideal transformer with variable ratio, multi-winding transformer, and three-phase three-winding, etc. All these transformer models are available. Similarly, transmission lines like a distributed transmission line, single-phase Burton model, three-phase Burton model, and 5 sections, RL section, transmission line, and underground cable. Okay, so all this required for modeling part is available in our library. So now we are going to develop a model for a single phase inverter. So first of all, we'll start taking the components which I require. So I require a source first. So I'll go to the sources library and I'll drag and drop a voltage source over here. If you have any query, you can unmute yourself and you can ask. Okay, else you can write also the query in chat box. So first of all, I have drag and drop a voltage source over here. Now I'll go to this converters part and I'll drag and drop a single phase inverter because I'm going to develop a model for single phase inverter. So I'll just drag and drop single phase inverter. I'll zoom out a little bit for my convenience. Now I'll take some passive component. So you can click on this passive component. I'll take the capacitor over here. And for filtering purpose also, I'll take a capacitor and an inductor. And for load, I'll take a resistor. Okay. So all the components which I require is available over here. Only thing I miss is the measurement part. So for measurement, I will take voltage measurement for measuring the voltage after inverter and after load, and also a current measurement. Okay, so I just drag and drop and place the components. Now, whatever the thing I required for developing and modeling of a single phase inverter is already available over here. So you can see, I'll just reconfigure this part. So if I want to rotate it, I can use this option, or you can use Control plus R. So like I have pressed Control plus R, like this both ways you can rotate this library components in this manner. Similarly, I'll place the components properly. So I will rotate this voltage measurement using this way, or you can use Control plus R. Similarly, you can rotate it. And over here also. Okay. So I have placed all the components line. Now I need to connect. So first of all, take your cursor to this green button. Whenever you take your cursor, place your cursor onto this green button, you need to, a red color will appear over here. You need to click on it. A plus sign will appear like this. Do not drag. After clicking, do not drag. Only just remove your cursor and go to the point in which you want to connect, and then again click. So first of all, go to this green button, click over here, and again go to this part and click. So like this, you can connect the component. No need to drag like Simulink. You used to drag. So like this, no need to drag. First, go to this green button, click over here, and go to that part in which you need to connect, and then click. Okay. Just you need to press one click over here, and then come to this point in which you need to connect, and then click. Okay. No need to drag. Similarly, I'll connect all this component over here, and this part also. And I'll connect the resistor and this voltage and current measurement block like this. Okay, so my connection is done. Now I need to provide the values. Okay, I will not provide the values for this voltage source because I am going to control this voltage source online while running simulation by using SCADA widgets. So I will not provide any fixed value for this voltage source. Okay, I'll provide this values for this component, for this capacitor. So if you double click on it, you can see capacitance 1E minus 6. So I'll just provide some random values. Okay, so if you want to see the details for this single phase inverter, you need to click on this single phase inverter, and you can go to the click options, and over here you see this is the internal circuitry of this single phase inverter. Okay, I think Mr. Sampath, you have got your query, answer for your query. Yes, there is a requirement of additional kitting, how you need to give pulses for this inverter. Okay, so for that I will demonstrate. Okay, when I do modeling. First, let me complete the circuit part first. Okay, so over here I'll just provide random values for this capacitor. Just provide here 100E minus 6. Okay. Similarly, if you want, I want to provide values for this inductor. So I can provide values here, or I can write it on this model slicing script. So let's take an example. I have typed over here inductance value as L, and over here capacitance value as C, and resistance value as R. Okay, so I define the values over here. Now I need to provide the values in this part. So I have just just click on this model initialization function over here. and over here I'll just provide the values. L equal to 10 minus 6, C equal to 100 minus 6. I'm just taking random values. R equal to 10. Okay, so you can define the values over here. Mr. Ranjit, after session I will connect with you via NetEase and we'll see that issue. Okay. So I provided the values over here. Now I need to provide the heating pulse in this single phase inverter. Okay. So I'll just double click on it, and here you can see the control option as digital input per switch, digital input per day, internal modulator, and model. Okay. So what is the difference between all these four control options we are going to discuss? So first we'll go with this digital input per switch. If you click on this digital input per switch, you can see it's written as SA top, SA pod, SB top, and SB pod. What is this SA top and SA pod? If you go back again to this documentation part, you can see this top switch is SA top, this bottom switch is SA pod, and this one is SB top, and this one is SB pod. Okay, so just a moment. Yeah, so you can see SA top, SA pod, this switch, and SB top and SB pod. So this switches are over here, name is over here, and I need to provide the controller pulse to the switches. So if you have developed any controller outside the simulation, outside this simulation software environment, so you can provide the pulses, PWM pulses for these switches by clicking on this. You can see 1 to 32 digital pins are available over here. You can select the pin configuration and you can provide the signals onto this respective pins. Okay, so that means you can control the inverter from outside using this switching configuration. Else, right now I am using only the software, so I'll just manually control the switches. So let's discuss about how. So after I develop a model, I'll just press on this compile option over here. Okay, compile and open model in SCADA. So I'll just use this option, and after I click onto it, it will ask me to save. So I'll just give it the name test and then save it. Okay. So here you can see this Windows console is running, and you can see over here. You will see over here it will say compile, compiling. Okay. So the model is compiling, successfully compiled. After the model is compiled, it will open like this. You can see over here it is written as HIL SCADA, and it will a pop-up dialog box will appear over here, like it is asking to connecting device unable to connect to the hardware device. What should it do? So whenever we are running with the simulation software only, we are not connected to any hardware device, we need to click on this part, load model to the virtual device. So if you click on this, it starts loading the virtual device. Virtual device means it is currently preparing your computer or your laptop as a real-time simulator. Okay. So let's wait for some time to load the model. In that meantime, I will go back again to the schematic editor. I'll discuss this message console part. So whenever you are designing a new type of model, if any error comes, it will appear over here that this is the error in your model. Please try to rectify it and then again compile. So over here you can see schematic is prepared, validation passed, and HIL 0 as we are using only one single HIL device over here. So it's saying HIL 0. And what are the components we have used? You can see the details onto this part. Number of core we have used, 1 out of 3. And the rest of the sources utilization we have used over here. The details you can see. And the time step we have used for this model is 5t minus 7 or 500 nanosecond. Okay. So all the details regarding the model and the, yeah.
So what does this mean? Bad voltage loop consisting of VS1 and C detected. What does that mean actually?
Hello.
Sir. Hello?
Yes.
Sir,
Yes,
can you
yes,
hear
yes.
me? So
Yeah,
what
yeah,
does
I
this
can hear
mean?
you.
Bad voltage loop consisting of VS1 and C1 detected. The passive capacitor component may be degenerated. So does this affect our real simulation in, like, will
Yeah,
it cause any
sometimes
problems or instability in
sometimes
calculation?
it causes unstability. Yeah, sometimes it causes instability. Okay, for that we need to provide the proper capacitor voltage values. Okay, or else if you're using any core coupling part inside this model, okay, for that we need to keep proper snubber values, else sometimes it creates issue in result part. Okay,
Actually, this is about what you are talking right now. In this model, the controller is not used. First thing. Second thing, the placing of component, that where you want to place the particular components. So the position and situation both are going to affect the converter switch voltages. Like in this, I think this is the single phase inverter model. So there is a if you draw the truth tables, so you will get 100, means we will start from 001 and then 1010, so like that. So that particular if you count the number of state space matrices which are going to form. Okay, so this model having 4 switches, so there is going to 2 to the power 4 state space matrices going to be formed. So accordingly which matrix combination is going to affect by not having the particular component position or something like that, is this is showing into here. Right now this is just the warning. This is not going to affect the means your modeling or anything else. I hope you got the answer.
Yes, sir. Thank you so much.
Okay.
Thank you, Sansar. So I'll just move back to the SCADA part. My model is loaded on this field SCADA. So as I have designed a new model, so I need to create my own SCADA panel for this model part. So I just click on this create new panel. So a new dialog box will appear over here. You can see a blank page will appear over here, and this is the SCADA widget library. Okay, so if you cannot view this SCADA widget library, you need to go to this view section and you need to enable this. Okay. So over here you can see the various SCADA widget library available over here, like action widgets, monitoring widgets, and data logging, connection, and visuals. Okay. So action means if you want to provide any type of action inside the simulation, like slider, knob, or if you want to provide any timer sections inside the simulation, then you can use macro, button widget, text box, combo box, etc. Like if you change the slider values, you can change the voltage or any other parameters, etc. So for this, we have named it as action widget section. So whatever you want to change inside the simulation, you can use this action widget library over here, and you can use that. Similarly, for modeling purpose, you have this gauge, digital display, text display, LED, trace graph, XY graph, phasor graph, PV monitor for monitoring your PV panel and tracking the MPPT, and capture scope. Okay. Similarly, for data logging purpose, you have the signal data logger, which logs your data in .csv, .mat, TDMS format, and streaming data logger. If you want to send that log data file from one place to another, a distant place, you can use this streaming data logger, and you can stream the data from one place to another using some kind of communication protocols you want to use. Similarly, if you are doing controller hardware in loop simulation for connecting your controller with SCADA part, you need to use a serial and you need to connect your controller, okay, the COM port especially. And similarly for visuals, you have this group. So if you are using multiple action or monitoring widgets, you can use group and you can merge it to one. Similarly, here is a panel, text note, and image. If you want to insert any image inside this SCADA part, you can use this option. You can drag and drop and select the image and you can go with it. So for this, I will just use a slider for changing my input voltage, and I'll take a capture scope for viewing the waveforms, and I'll take a digital display for my currents, and a gauge for measuring the voltage. Okay, so this is all I required basically. If you want, you can also add various monitoring widget or action widgets as per your own requirement, and you can use. Now I need to select the signals which I want to use, see onto this digital display or this gauge. I need to select the signals. So first of all, I need to configure this digital display. So I'll double click on this digital display. It will open like this. Name, I'll provide its name as I out. Okay, and I'll select the signals. So I need to click on this analog signal, and then I need to scroll it down. I need to select the signals. So here is my signal IA1. Over here, if you go back to this schematic part, you can see it's written over here as IA1. Okay. So whatever the name you provide over here, it will appear in the SCADA part. So you can see this IA1. Similarly, I will use it for V output. So V out, and select the analog signal. Just click onto it, slide it down, and this is my signal I want to see over here. You can see this VA2, and similarly, I will click on this capture scope, and I'll select the signals which I want to see the waveform. So I'll click on the signals and then click on plus. So first report I will use, first signal I will select voltage source, my source voltage, and then I'll select my first inverter voltage output, and then VA2, and then my current. Okay, so I have selected these signals, and now I need to select the viewport, in which viewport I want to see the signals. So I'll use PS1 on first viewport, VA1 on second viewport. So you can see another viewport is created over here whenever I have taken this VA1 to the second viewport. Similarly, I'll take VA2 on third viewport, and this IA1 on fourth viewport. So similarly, whenever I selected this fourth viewport, you can see these four viewports are already created over here. Okay, so I have selected the signal, selected the viewport. Now I'll close this button, and now I'll configure my slider. So this is the important point. You must see or note it down. Okay, so now I'll double click on a slider. I will use slider to control my voltage source. So I just change the name of the slider first as voltage source. Now I'll select the slider properties, minimum and maximum values. So I just want to change my voltage value from 0 to 200. So I'll make it maximum as 200 and step of 10. Okay, so I have selected the parameters for my slider. Now I will need to configure the slider for voltage source. So for that purpose, I need to go to this editing code editor section. So I'll click on this editing code editor. It will open like this. Okay. So I want to control or configure my source. So for that purpose, I need to go to this control command. Then I need to go to the source settings, and over here you can see VS1 constant. If I want to use constant, then I can use this constant part. If I want to use sine or arbitrary, means whatever the waveform I have generated from this waveform generator, I can use over here also. So for this part, I need only constant, and I just place the cursor on line number 3. You can see I have placed my cursor, and I will click on insert. So whenever I click on insert, a code will appear over here. You can see l.set underscore source underscore constant underscore value, signal name as VS1, you can see, and value equal to 0.0. Now, as we want to control my voltage source from the slider by just dragging the slider, So over here, I need to change this value 0.0. I just remove this 0.0 like this, and I will type over here IN. So whenever I type IN over here, in small, it will appear like this input value. So I'll just click over here, and it will be automatically pasted in this macro code options. So after I pasted this input value option, I need to save this code, and I'll close this one. So my slider is configured properly. So if anyone is having any doubt regarding this configuration of slider or want to repeat it, you can unmute yourself and you can see. You can ask for that purpose.
Sir, do we have to
Is
say
there
input
anyone?
value, sorry, value equal to input value, or you can just say input value?
No, you will need to write value equal to input value.
Okay, sir. Thank you.
Anyone? Okay, I think there is no one left. So I have configured my slider for changing my voltage source. I have configured my digital display for taking out my current value, and I have also configured my this gauge for measuring this voltage values, and also I have configured this capture scope for viewing the waveforms. Now what I will do, okay, so I just start the simulation. So over here you can see everything is coming 0. All the output is coming 0 because we have not provided any source value. So I just change over here to 100. So you can see base one is coming 25 per division, 25 volt per division. Okay, so that means 100 volt is coming, but we are not getting any output because we have not provided any pulse to our switches. So for that purpose, we'll go to this switching blocks in model controls. So you can also change your sources from over here. You can make it 60. So whenever you are providing any values, you need to provide the values over here, and you need to press enter. So until and unless you press enter, this value will not be inserted inside the simulation. Okay. So I change the values from here as 60. So you can see overriding this slider and providing the values 15, 40 volt per division. So I'll go to the switching blocks. So if I click on switching blocks, you can see the switch name SA bot, SA top, which I have shown in the help documentation for this single phase inverter. So I'll take this software control. So I'll take the software control of all the switches, and now I'll manually turn on and off the switches. So first of all, I'll turn on this AC top switch, and then ASB bottom switch. Okay, so now you can see some output you are getting over here. So like this, you can form your truth table for your if you want to design your new type of converter. So by this manner, using this software control and a manual switching, you can generate the truth table for it. Okay, so let's take I make 0 and turn on this bottom switch and this top switch on. So similarly, we are getting the negative. Okay. So by this manner, if you want to develop, if you have not developed any controller, you can test the feasibility of a new type of converter which you have designed by using this software control options. Okay, so I just turn off all this software control, close this part, and I'll stop the simulation from here, the red button over there. Okay, so now I'll minimize it and go back again to my schematic section. Okay, so now I'll change the control option, and I'll change the signals also. So I change the signal name as input voltage, and over here as D inverter, and this one as D out, and this one as I out. Okay, and now I'll change this control option from digital input per switch to model. So I've tested this digital input per switch. Now I'll select model and then click on OK. So you can see only one option is available over here. So I need to provide pulse for these 4 switches using this control options. So I develop the controller for this single phase inverter. So for that purpose, I'll take sinusoidal source. So I'll go to the signal processing sources. I'll take a sinusoidal source and I'll take a triangular wave source and I'll take a comparator and I will, or a relation operator, I will better take. So I'll make it greater than equal to. This is my reference signal and this is my carrier. I'll use triangle as my carrier. So I just connect the signals over here like this manner, and now I'll take a logical operator and make this not of a signal. So I just change it to not. And now here is my 2 signals for my leg A, top and bottom switch, and similarly I will generate another 2 signals for my leg B. Okay, so I just copy it and paste it over here. And now I'll provide the parameters for the sinusoidal source, amplitude 1, phase 0, and execution rate I'll make it as TS. Similarly, for triangular wave source, I'll make the minimum value as 0.9, maximum signal value as 0.9, and frequency as 4000 Hz, and duty cycle as 0.9, and execution rate as TS. Okay. Similarly, for sinusoidal source, I'll only change the phase. I'll make the phase as 180 degree and execution rate as TS. And I'll change the value for this triangular wave source. Similarly, for 0.9 maximum and frequency as 4000 Hz and duty cycle as 0.9 and execution rate as TS. Okay. Now I'll take a bus joint. So I'll just type over here find component as bus, so it will come appear over here as bus joint. So I'm getting these 4 signals, so I'll double click on it, make the number of inputs as 4 and then click on OK. So now I'll connect this output to this single phase inverter, and now I'll take this signal one by one. This is for my top switch, this is for my bottom switch of leg A. Just a moment. Yeah, like this manner. Similarly, I'll take it from here and connect this bus joint port 4 and this logical operator with this part. Okay, so I have provided this 4 signal to my 4 switches over here in this single phase inverter. Now I will provide the value for my execution rate in this model initialization. So I just type over here TS equal to 200 T minus 6. Okay. So now I'll again compile this model. So I just start compiling by clicking on this compile and open model in HIL starter. So let it get compiled.
Sir, what is the difference between the simulation time step and TS1?
Actually, in Typhoon HIL, you need to provide 2 time steps, one for this planned part and another one for this signal processing part. Over here, when we have developed only the planned part, we have provided the TS part when we are configuring this schematic settings over here. Okay, in simulation step. And this is all those are signal processing components. Means in Typhoon HIL, You can see this plant part is represented in black color, and this controller part or signal processing part components are represented in blue color. So these are all my signal processing components, and if you double click on it, you can see the execution rate as TS we have mentioned. So in Typhoon HIL, there we need to provide two types of execution rate or simulation time step. So for that, we have defined over here TS equal to 200 minus 6 for our signal processing components. Okay, and for plan part, we have defined it as when we start the create the new model as 500 0.5 microsecond. Okay, so I'll just go back to the HIL SCADA. My model is loaded, and now
Sir,
I will start.
sorry
Yeah.
to disturb. So my
Okay.
my problem is, suppose if I have a digital controller, so sampling time, what should I take? Should I take simulation step or should I take the TS as a sampling time?
You should take TS.
TS should be the sampling time, not the simulation step.
No. The simulation step we are provided over here is for the plant part, not for the controller part. So if you are taking any digital controller, so you need to provide that value in TS, whatever we are defined.
Okay, sir, thank you so much.
And let's take an example. If you are using an external controller to connect with the plant part which is running in Typhoon HIL, for that you have already defined. Okay. Okay, so I'll just my model is loaded onto the HIL SCADA part. I'll just again click on this run start the simulation button over here, and I'll provide the voltage source over here. Okay, just a moment. I need to select the signals. Actually, I have not selected the signals. Okay, so I'll select the signals as input voltage and V inverter output voltage, and then V out, and then my current output as I out, and I will just take out to the viewport. Okay, and similarly for this I need to configure again because I've changed the name for this VS1. So I'll just delete this line, and I can go back to the editing code editor and show settings, press the cursor over here and then insert. Similarly, I'll change the value in equal to 0.0 to input voltage, input value, sorry, and then save this. So my code is ready. And I will need to select the signals for this output voltage as V out and this one as I out. So actually I have not designed any proper controller for that part. So you are getting this kind of results. Okay. So I just stop simulation, and now I'll go back once again to the schematic editor and change this control option for this single phase inverter to internal modulator. And over here, when I select internal modulator, you can see this option as fixed carrier frequency, and you can see variable carrier frequency. So if you have, if you want to use fixed carrier frequency, you can go with this option, or if you want to use variable carrier frequency, you need to select this. So when I select fixed carrier frequency, you need to select provide the carrier frequency as I'll provide 4000 Hertz. Yeah, definitely you will get the video of the presentation, also the recording link of this presentation. Okay, and I'll provide the data template as 1E-6 and click on OK. Now you can see there are three input ports available over here as EN, INA, and INB. Okay, So now the carrier is already inbuilt inside this single phase inverter. Now I need to provide only the reference signal for leg A and leg B. So I'll just delete this part and this part as well. I require only sinusoidal source because these are my reference signal. Okay, so I'll provide the sinusoidal source to leg A, input A, and this one to input B. So now you can see this EN port means enabling this single phase inverter. Either you can use a constant or you can use a SCADA input for that purpose. So I'll use a constant and I'll connect it to this EN port. And in constant, I'll change the initial bit as yes. Okay. So now I'll just run this simulation.
Yeah, I have one doubt here.
Yeah.
Why you have removed that triangle and sine comparison? Directly you are giving sinusoidal wave in the phase.
Yes. Because at the time we are using one reference signal and one carrier signal. So for carrier we have used triangular wave source. Now when if you double click on it, I have changed the control option. Previously we are using model. Okay, I just go back once again. Previously we are using control option as model. Now we have selected it to internal modulator. So whenever you have selected internal modulator, you can see the carrier frequency is already over here. So we have provided the carrier when we select the internal modulator, the carrier frequency is already inbuilt. We need to provide only the reference signal. So for that purpose, we have provided the reference signal only to leg A and leg B. Okay, I think this is clear.
Okay, thank you.
So we'll again back to this HIL SCADA part. Yeah.
Excuse me. So in the new Typhoon, we have also another option which says internal modulator separated. What does that mean? You have digital input per switch, internal modulator separated.
Actually, I'm not getting the idea what you're talking about. Can you share the screenshot later after the end of the session?
Okay, sir. Thank you.
Yeah. Okay. So I'll just now run the simulation once again. Okay, now I can see the inputs, outputs are coming. So this is the difference. Okay. So I'll just close it down and save all these files. So in Typhoon HIL, there are three types of file. One is this .cus, means whatever the panel you have designed, the digital displays and the gauge you have used, you need to save that file also, as well as the model you have designed. So first in .cus format, you can see we have saved, and this is my .tsc file. Okay. So now I'll just run an example model for mppt PV inverter. So before that, I will generate a PV file. So for that purpose, I'll go to this waveform generator. I just open this, clicked on this waveform generator. Let it get opened. Okay, so you can see there are options as mode, generate PV or import IV. If you have any IV data, you can call it. If you click on this IV, import IV, you can call it. If you have any .clc data, you can use this import form, and you can go to that link and you can call it. Else, if you want to generate your PV, so I want to generate my PV, and it's asking for import model, detail EN50530 compatible, normalized IV type. So I'll go with this EN50530 compatible. Else, if you want to go for detailed modeling, if you know all these values for VOC, ISC, IC, number of cells, type of cells, and identity factor, okay, like CSI, amorphous silicon, you can select all this for detailed. Else, you can go with EN50530 compatible. You need to provide only this VOC and IC values and type of film, CSE thin film and user defined. You click on user defined, you can provide this technology settings value also. So I just go with this CSI and you can provide this irradiation and temperature parameters over here and then click on preview. So whenever you click on preview, you can see this maximum power as at 213.28 watts and current and PI values. So you can preview your PV curve. So if you want to save this data, you need to click on this part. So I'll save it on desktop. I'll give a name as Anurag PV and I'll save. Okay. So my PV settings file is set. And if you want to generate your own source file, you need to go to the source file generator and you need to click on this plus. You need to select the type of signal like sinusoidal, DC constant, sawtooth or square. So let's take the sawtooth and provide the amplitude as 50. So whenever you are entering any values, it will be on red in color. I'll repeat once again because many of you face this problem. So whenever you provide any value, it will be red in color. You need to provide the value and then click on enter, and then you can insert the signals. So I have provided the signals over here. And if you want to make any changes onto this, you can use these options. And you can make the changes. Like this. And you can save the source file. You can save the source file. I'll save it on desktop. It will be saved in .ig format. I'll even name this as Anurag test, Anurag source, and I'll save it. Okay. So I've generated one source file from using the source file generator, and I've generated this P file from this PV generator. Okay. So these are steps that how we can use this Typhoon waveform generator. Now I'll close it. So now I'll open an example model for, so these are the steps to how to open an example model. First, you need to go to this file and then go click on this open example model, and then I will open the example model for MPPT boost charger. So I'll go to this general power electronics, else you can see the example models available for every domain like aerospace, automotive, basic electrical circuits, connection protocols, electrical drives, general power electronics, gate converters, hardware in the loop, how to example marine power systems, microwave power quality, power supplies as well as power systems. So if I need to open this MPPT boost charger model, so I'll just double click on this MPPT boost charger and I'll open this model. Over here you can see this model for this MPPT boost charger. I'll zoom it a little bit. You can see this PV photovoltaic panel we have used, but we have not defined the type of panel and irradiation and temperature conditions over here. I have taken this measurement blocks IPP and VPP, and here we have used boost converter, and we have taken this VPV and IPP values for measuring the del P and del V. So we are measuring the difference, and over here we are using it for P&O algorithm. So the P&O algorithm, we have taken this power and voltage input, and in output we have taken out and variables, duty cycle, delta duty cycle, minimum value, maximum value, and step, as well as we have written the functions, P&O algorithm functions over here. If power equal to 0, step equal to 0, and then over here out equal to duty cycle. We are taking the duty cycle as our output. Okay. So you can write the codes over here. It will be in C format, and you can check the syntax by clicking on it. You can see no errors found, and then click on OK. Similarly, over here we are taking SR flip-flop logic for turning on and off this boost converter. Over here, we have placed an V output and we are taking the V output signals on this comparator. We have taken this battery upper limit for charging and discharging. So we're taking the battery lower limit as 49 and upper limit as 2. And we are comparing it with this measured voltage output signals over here. And we have used SR flip-flop logic. And from SR flip-flop logic, we are taking this Q signal for enable. Enable signal is going to this boost converter for enabling this boost converter. Okay. And over here we have used this battery for charging, and these are the loads. Okay. So now I'll just compile this model. So I've just click on this compile and open model in Startup. Let it get compiled. Okay, so now again it will ask us to this option, load model to virtual device. So I'll click on it. So we'll wait the model to get loaded for virtual HIL device. Okay, so now our model is loaded, and as we have opened the example model, so you can see it is already there, mppt push charger.cs panel found in model directory. So I'll click on to this. So you can see the PV panel is already over here. So now I just start the simulation. Okay, so now you can see PV is tracking, PV model, we're tracking the MPPT. Now if you want to change the irradiation, you can use the slider option for changing it. So we will make it to the 1000. So whatever the thing is it, you can change it online while running simulation. You can see our simulation is running. Okay. And now if you want to provide any new type of PV file over here, so you need to go to this PV and you can select on this load PV. And if you want to provide any shaded PV type, so you need to click on the shaded PV example, and you can see this file is already imported. We have not stopped our simulation, it is running. You can see this time is running virtual HIL mode. So without stopping any simulation, we have provided our PV file over here. Also, now we'll just load the PV which we have generated today from waveform generator. So we have saved it on desktop. So we'll go to the desktop and select this PV as anurag.pv.ipvs and provide the illumination. You can change this. Okay. So like this way, you can do the PV modeling part also directly and without stopping the simulation. So if you have any queries, any question regarding this model and regarding the SCADA panel, you can ask. I'll be happy to answer you. Else we'll move forward to our next model demonstration. So is there any queries from your side?
Hello,
okay.
sir.
Yeah.
Vipo, can I get this video of this one recording video?
Definitely. We'll provide the video link. I think yesterday video link is also been provided in WhatsApp group.
Yeah,
Professor Venu Madhav has shared.
Due to internet problem, I haven't been to some of these points, whatever the madam shared yesterday. So today also in the every session been somewhat internet problem, so I didn't come to after. but I'm on the way. What I came up to now, but I have to get that thing. So I can
Sure.
possibility of
So after the
queries we can post you directly.
directly, yeah, you can post us directly, and we'll provide the YouTube video link of this session also. After the end of the session, we'll provide the YouTube video link as well as the recording link in GoToWebinar format. Okay, so no issues regarding that. You will get all details. Okay, any other queries? Any other queries from anyone?
We can simulate all the types, or only we can modulate the problem things for power systems.
Yeah, you can simulate. You can do
Okay,
analysis part also, and
the model examples. Can we take it that one and we can overwrite over that one, or can we have to do the same thing?
if you are overwriting an example model, it's better suggested that you just first create a new model. Just like I have opened here, you can see this is the model which I have designed, and this is the example model which I have opened. So it's preferable that you should first copy this model by pressing Control and Control C, and then go to the new model section and paste it over here and do the rest of the part.
Okay.
So if you make any changes, then it will affect the example model and it will not reopen the same again. So it's preferable whenever you are just working with an example model, you just open a new model and then paste the example model over there and then start working and see the results. Okay. And in the meantime, if you face any kind of issues, any kind of errors, you can contact us directly. There is no issue for that.
Sir, example problems are not locked, like means if we do changes in the example problems, it will save?
If you save, then it will save. If you do not save, then it's okay. But it's preferable
usually
if you are
MATLAB, I think in Simulink, the example problems are locked. You cannot change them.
No. Here the example models are not locked. You can work with it.
Okay, sir. Thank you.
Okay. So I'll just move to the our next example model. I'll just close it. Let's close the startup part also. As usual, I'll just stop the simulation. Okay. So now I'll open another example model. I will again go to the file, open example model, and then grid current converters, and then I'll open grid current converter PQ. So let it get some time to open. So here is our model for our grid current converter PQ control. So if you zoom it, so you can see we have used a DC voltage source over here. To double click on it, you can change the source nature as constant sign over here also, or else you can change it from SCADA part directly. Okay, as I have used for the single phase inverter, you have seen. We have used the CDC DC link capacitor and VDC voltage measurement and three-phase inverter. We are taking this modulator signals for leg A, leg B, and leg C. We are giving this reference signals, and already the carrier is inbuilt. We are taking the carrier frequency as 4000 Hertz. Dead time period we have selected. Now here we have used LC filters over here, and similarly we have used the measurements, and this is our three-phase voltage source which we have used as our grid. Okay, so here you can see two grid impedance we have selected. One is for strong grid, and another one is this for weak grid. So we have changes the values R grid, and here you can see LCA, and we have provided all these values over here in this model initialized function. We have selected the simulation time step, R values, and here you can see L grid equal to 5e minus 6, and R grid equal to 10e minus 3, and L grid equal to 200e minus 6. So all the value which is provided inside it is defined over here. So this is for strong grid and this is for weak grid. We will change the impedance over here using this contactor, and we have used this measurement parameters. From here we are measuring this VA, VB, and VC, and IA, IB, and IC. And if you go back to this controller part over here, we have used this VA, VB, and VC to generate our VD, VQ, frequency, and omega T over here. You can see Now over here we are measuring this power. We are taking out power P, Q, S, EF. So we are taking input as VA, VP. This to click on this measurement. We have used this power measurement, power meter, and we are measuring this PQ, S, and EF. Okay. We're taking input as VA, VP, and VC, IA, IP, and IC. So I'll zoom it back again. So over here you can see for ABC to PQ transformation we have take this IA, IB, IC and change it to ID, IQ, and I0 by ABC and DQ transformation. Similarly, for current reference, we have taken this P reference and Q reference. We are taking as a SCADA input by which we can change online while running simulation. And over here, we're taking VD and DQ input. Over here, we are generated the reference value ID, ref, Q ref. And over here, we are getting this ID, IQ values. And in controller, current controller, we are using PI controllers inside it. Click on it. We are using PI and we are measuring the difference between ID, IQ and ID, IQ reference. And then,
sir, excuse me, sir, just one small question in the PI controller.
Yeah.
Can you double click on the PI controller and open the?
Just a moment. Yeah.
Can you open the parameters of this PI controller, sir?
Sure.
No, here, sir, this KPKI.
Yeah.
Usually we use continuous algorithms, like in analog form. We find the values of KP and KI. No, but this is a digital PID controller, is it? This is a discrete PID controller.
Yeah.
So suppose if I use an algorithm to find the values of KPKI, do I need to change this KPKI into discrete form? Or I can use the KPKI that I found using the normal Bode plot or
yeah, you can
root
use that
locus, whatever algorithm I have used to find the values of KPKI. Can I use the same values as it is, or do I have to discretize them using the sampling time and all those things here?
One thing I'll tell you that whenever we are talking about real-time simulation, we need to discretize everything because there is no continuous formation for that. Okay.
But I have a HIL device. We have analog channels in there. So I will design my controller in D space, which is a very fast controller. So even if I don't discretize it, it's running in a very high speed. So can I use analog pins on the HIL device and use KPKI as it is?
Yeah. You can use that part also.
Now
but
here
in general,
this KPKI, are these discrete values or are they the normal KPKI values that you find using Bode plots or root locus or Nicholas-Ziegler method, any method that you use to find the KPKI? Because sir, I have designed a PI controller and it's not working as it is.
Okay, so you are designing Typhoon.
There are two things. First thing is the continuous domain analysis, and the second thing is the discrete time analysis. Okay. Yeah. So when you are doing normal simulation, like in MATLAB or normal simulation tools, so there you will find option to perform continuous time simulation. But yes, when you talk about the real time simulation, there is everything need to be discretized. Only then you can perform real time simulation. And you are talking about the D space controller. So D space is the interfacing element. Okay.
Yes, sir.
Now, as you want to give the analog values to the disk PI controller, you can give analog input are available into Typhoon HIL devices. You can provide your analog input values to disk PI controller.
No, sir. Actually, my problem is my PI controller is sitting in DSP, the D space. I'm not using the PI controller of the software. I'm using it. I've built the PI controller in the D space. I've generated the control signal. Can I pass this control signal to the analog pin, or do I have to pass it to a discretized digital pin?
You need to give that signal using analog pin.
Using analog pin, not using digital, right?
No, analog pin.
Okay, sir. Thank you.
So you can.
For that purpose, what you have to do, we open the PI. Sudipto, please open the property of PI.
You need to change the source as external.
Sudipto, can you please open the property of PI controller?
Yeah, I have opened.
So in that one, select the external.
Yeah, already selected, and after selecting external, point will be available over here. You can take this analog input signal, like I just take the analog input signal, analog input over here, and you can connect it with this KPI. Okay, and over in this analog input, you can select the pin number in which you are taking the signal from DSpace.DSP controller, and you can provide it directly. Okay, so I think this is clear.
No, sir, but in real life scenario, because this HIL device is still a simulator, but in real life device, I have a real inverter in my lab. I will test it on the HIL using DSpace controller. Can I take the DSpace controller and directly connect it to my actual hardware inverter? Because I will not be having this PI in my hardware.
At that time,
You can take out the control signal from HIL device and you can connect directly with your converter.
Oh, okay, sir. Okay, thank you, sir.
Okay.
So I just putting this back again. Okay. So again, I am transferring this TQ to ABC over here, and we are generating this ABC signals and providing this ABC signal to this three-phase inverter. So, is there anyone is having any doubt regarding this model? Ask. Okay.
Sir,
so now
if there is no much work, can we change, like, at least for this example problem, can we change this three-phase inverter as a NPC type?
Yeah, definitely you can change. It's all upon you, but it's preferable.
I was just wondering if you can show it to us. We will change this in this example.
Okay, I'll just change it to NPC.
Because I think in that case, then you will have to use a core coupling also. So we'll get an example of core coupling also.
Okay, so like this, you want to replace this three-phase inverter, or do you want to use this NPC inverter over here directly? Means with this three-phase inverter.
I want to replace the three-phase inverter by an NPC type inverter.
Okay, so for that purpose, you just need to delete this part and place it over here. But here we are getting just a moment.
Because in any case, the internal modulator will generate the carrier frequency and everything. All we need to give is a reference signal. Those reference signals are also coming from the PI controller anyways. So I think it should work if we change this to NPC type.
For the better understanding regarding this, how to use the NPC converter, you just go to the electric drives examples and you will find there is one example V by S control. So there, three-level NPC type inverter is used. Okay. And see, it's not about the converter, it's about the weight of particular converter. So you need to count the weight.
So if you take this NPC type, then we may have to add a core coupling. So you can show us the core coupling example also. So that's what I was wondering.
Pardon?
Because now if I take the NPC converter here, I don't think it will simulate. You may have to add a core coupling to simulate it in different core now.
No.
Now this is the three-phase converter. Okay, and per core is having capability to simulate up to three-phase three-level converter. So when you are using NPC converter, you just need to check the weight. Okay, so this converter is having weight. You can simulate with one core.
Okay, sir. Thank you.
So I think this is clear to you.
Yes, sir. Yes, sir. Thank
So
you so
here
much.
using okay. So for when core coupling is required when you are using weight more than 3. Okay. So if you use another single phase converter or single phase rectifier, for that purpose you need to use a core coupling in between, and you need to separate the circuit. Okay. It is not
Okay, sir.
required
Thank you.
right now because we are using only a single converter over here, single phase converter. So I'll
Okay.
just go back.
Yeah, I have one doubt over here. Can
Okay.
we take here as a cascaded H bridge
Sorry.
in the place of the single phase inverter? Can we take cascaded H bridge inverter?
Yes,
Yeah,
you
you
can
can take.
take.
You can use.
Then how we can give the pulses? For that we have to generate the own pulses, or we can use directly over like you have used like that.
It's up to
Right
you.
now, when
If you want, you
exactly
can
right now,
design, or if you want, you can take the inbuilt pulses. And there is a SPWM modulator also there. You can utilize that one also.
Okay. Thank you.
Mhm.
okay, so I'll just compile this model
Sir,
over. Yeah,
sir, so every type we have different type of modulators. For example, if you want hysteresis current modulator, if we can use that also. Is there such type again?
yeah, you can. It is available also.
It is in special. It is from
Hysteresis.
SVPWM, space vector pulse width modulation, in which we are using hysteresis
Uh-huh.
current method. That is also possible from
Uh-huh.
here for
Yeah,
each.
it is
See, in
also possible.
SPWM modulator, that is inbuilt. But if you want to design your own, you can design,
Yeah.
and you can use not only hysteresis. In fact, other method also you can utilize that one. Okay.
Okay, sir.
Okay, so let wait for the model to be compiled and open it as SCADA.
Sir, one more doubt.
Yeah,
Sudeepo, is every time the
yeah, yeah.
compiler has to be loaded once again, and we have to see whether all the data is being corrected or not.
See,
Once it is,
if you are making any changes in this, if you are making any changes in the schematic part, you need to
yeah,
compile. Okay. So
okay,
if you do not make any changes in the schematic part, you do not need to compile.
okay,
Okay. So actually, the variable
okay,
elements is already available in SCADA. You can change it
yeah,
without stopping simulation or without compiling. But if you make any changes to the values of the capacity components or any other values or change the name, then you need to compile for that purpose. Okay.
sure. Then okay.
Just similar to of MATLAB, but the difference is that in MATLAB we use the probe, the capture option in the schematic part itself. But here we are using a different window for capturing the monitoring and action purpose part, which is named as HIL SCADA. So this is the basic difference between that and this one. Okay.
Okay.
So
Thank
here
you.
our model is being loaded, and right now we'll just open this example panel 5, which is grid converter PQ. So I just click on it. It's already inbuilt. It is being built by all these action widgets and the modeling widgets available over here. You can see we have used caption scope, phasor graph, some sliders over here. Also here we have used a combo box for changing pure sine to harmonics, as well as grid impedance selector from strong grid to weak grid. Similarly, we will insert the fault type as LVRT, HVRT, LFRT, HFRT. Types of fault duration. All these widgets is been developed using this widget library and also inject fault options. Okay, so I'll just start the simulation for it, and I'll just open this caption scope. You can see the waveforms. I have selected this IA, IB, IC, VA, VAB, VAC, and IDC, as well as ID and IQ values. Okay. So now, as Fazula sir, you had asked me about how you want to take out the signals for giving it to the actual converters. For that purpose, you need to go to this analog outputs. Okay, output controls, analog outputs, and HR0. You need to double click on it. You need to select the signals which you want to take out. So for converter, we need digital signals. So we'll go to this digital outputs, and over here we'll select the signals. First, we'll just enable it, and we'll take out the signals. Let's take this signal of 1, and we from digital output 1, and we can provide this top switch signal to our actual converter, and we can run it. Okay. So like this way, you can take out this digital output signals from here, as well as analog output signals from the simulation through the digital output and analog output pins of the simulator. Okay. So right now my simulation is running, and you can see the time over here. It's 2 seconds. As we are running in only simulation mode, it is slow. But when we are connected with the real-time simulator, this time will be exactly same as your clock time. Okay. So now I change the grid waveform from pure sine to harmonics. So you can see. Also, you can change the grid impedance from strong grid to weak grid. So I'll get back again. Now, if you want to inject any harmonics directly without designing any types of widget, so for that purpose, you need to go to the sources, and over here you can see the grid sine 124/60 Hz, and you need to click on this use harmonics, and then click on this dialog box for harmonics. And after that, you can select the harmonics, provide the PU values, and then click on OK. So now you can see the harmonic values is inserted. Okay. So if I disable it, it will get removed.
So one more thing.
Now,
in MATLAB, we can use THD, total harmonic distortion, for knowing how much of harmonics distortion has been taken. So FFT analysis will be present. Similarly, here is any such thing you can see?
Yeah, THD measurement block is already available. I have shown when I am displaying the library part. Okay, THD measurement block is already available. Now let's take an example. You want to capture the signals. Okay, so for that purpose, you need to change this scope to capture, because it's running in it is in running mode. So I need to capture it. So I need to click on this capture button and click on this get settings option, and then click on yes. So after I click on yes, all these signals which are selected on scope mode, it will automatically come over here. Now I need to select the time interval. So I'll just make the time interval as 1 second, and over here you can select the sample rate from 100 SPS to 1 MSPS. So I'll take 100 SPS sample rate, and let's take, I want to capture this data from initial seconds to the next 1 second. Right now you can see the time is running as 7 seconds. So if I press this post trigger option, it will start capturing from 7 seconds to the next 1 second. Okay, so means 7 to 8 it will capture the transition. But if you want to capture it from the initial, from 0 to 1, then you need to first stop the simulation and trigger it first, and then you need to start the simulation. So let's wait. Whenever the time become from 0 to 1, it will plot the data. As we are running only simulation mode, so it will take a little bit of time. But when we are connected with actual simulator, so it will be following the actual clock time. Okay, so you can see we have started capture the data from 0 to 1 seconds. You can see 0 to 1 seconds. And if you want to analyze, you need to click over here. You can see like this. If you want to go for FFT analysis, if you want to save this waveforms, you can click on to this option. Sorry, you need to click on to this option. You can select the signals. I've selected all, and select the type format CSV, HDFI, MAT for opening it to the MATLAB, TDMS, and you can export the data. Like this, you can save the signals. Similarly, if you want to save this waveform in image format, you can use this option, export to PNG format. If you want to go for this FFT analysis, you need to click on this part, select the base frequency and you can get your FFT analysis over here. Similarly, if you want to change the colors and waveforms, you need to click onto this and you can change the colors and solid line, dash dot line, etc. type of lines over here. Okay. So if anyone is having any query, yeah.
Yes, sir. Sir, when you're doing the HIL device, my system is very fast, right? Because the whole plant is running on the HIL device, but this scope and all are running on my PC. So will I be able to capture the actual incident on this scope, or do I have to use another scope, physical scope?
You can capture the actual part in the scope inbuilt, and if you want to see, you can also use the physical scope over there also. Okay.
Because why I was telling this was because our plant will be on the HIL. HIL is running on FPGA. They are very fast. They will be actually in real time. They will be running. But your scope, which you have just shown, is on my PC, and my PC may be slow.
Actually,
so will it
the
affect?
thing is
I'm just because I want to. Will I be able to capture all the events, or I may miss some?
No. If you are using real-time simulator and you are using capture and scope, whatever the time means, the data is coming from your real-time simulator itself. It is not running. The data is not running on your PC. So whatever the simulation you are doing, so that data, the results is coming directly from your real-time simulator to your PC. Okay, so there is no delay, no transition delay over there. Okay, so no need to worry about that.
Okay, sir. Thank you.
You use the signal to see in the actual scope, and you see in the capture and scope on your PC, it will be similar. There is no difference for that, and no transition delay also. Okay.
Okay, sir. No, because I was telling this because when you see the HIL SCADA, you have this TSO, CIO. So TSO is time slot of the HIL device, right, sir?
Exactly. If something happens, if your model is overrunning the time step you have provided for the FPGA or the plant part, so this TSO error will occur. Okay.
What is the CIO then?
This is for signal processing part. Means as we have defined two time steps, one for the plant part and one for this controller part. Okay. So in actual, if you are using Typhoon simulator, the plant part is running on FPGA and the controller part is running on CPU processor on the simulator. Okay. So if whatever the time step we have provided for the controller part is exceeding, then this error will appear, CIO error.
So the CIO, the CPU is that means HIL device also has a CPU inbuilt. So it will not be using my computer CPU. It will be using the CPU inbuilt in the HIL.
No. You're not understanding the basic thing. See,
yes,
in Typhoon HIL, there are two types of processor. Okay, one is your FPGA, which is having some types of code, whether it is 6 series, then it will having 6 cores of FPGA, and it will having two CPU processor also. One is ARM and another one is microplace. Okay, ARM is one is user defined and another one is system defined. Okay. So now, whatever the means signal processing components or whatever the controller you have developed in Typhoon software, it will run by this user-defined CPU. Okay, and whatever the plant part you have designed in Typhoon HIL, it will be executed by the FPGA on the Typhoon. So whenever
this will be decided directly by the Typhoon itself. I don't need to mention this.
Exactly. No. You do not need to mention. It will automatically configure. Okay. There is no need to manually do all these things. And the thing is that
all this DQ to transformations and all this acquisition, everything will be done on the CPU, and the plant will be on the
on the FPGA part.
FPGA part. Okay, sir.
Yeah, so whatever the black color components available in Typhoon HIL will be run by FPGA, and whatever the blue color components will be run by our user-defined CPU. Okay, and one thing, whenever you're connecting with the real-time simulator, it will be directly load all these things into that simulator. So there is only the display and the monitoring actions will be performed by our laptop or our computer. Okay.
Okay, sir.
Only
Okay. So
while
nothing,
using our,
no resources from our laptop will be used when the HIL is running.
exactly, there will no resources will be used from our laptop or our computer. At that time, all the resources is being used from our real-time simulator. Okay. So all the calculations, all the data processing part is being done by our real-time simulator, not by our laptop. But when you are doing only simulation, all this thing is being performed. Whatever you have developed, all these things will be performed by our system CPU. Means whatever Intel Core processor we are using in our laptop, it is being performed by that only. Okay.
So if I am correct, sir, if I am correct, to coming back to this time step thing, so the simulation step will be done by the FPGA, and the TS that you have defined will be done by the CPU of the HIL. Is it correct?
Yeah, exactly what I was talking about at that time. It is the time step of the CPU of running inside the Typhoon HIL simulator. Okay.
Okay, sir. Okay, sir. Thank you very much, sir.
I think it's clear.
And
Okay,
sir,
so
I think you have missed yesterday's lecture. So I request you please go through the yesterday's lecture. You will find more depth detail about these things.
yeah,
Okay,
exactly.
okay, sir. Sorry. Actually, I was there, but I couldn't understand at that time. Sorry.
It's okay, no
It's
issues.
okay.
Any further queries? Someone is asking something. Yeah.
yes, so
Yeah. Tell me, sir.
here we are using the three-phase, no, the whatever the grid connected system. If we have
Exactly.
it, only the DC supply and we have got three-phase output, so PV have been taken. Yes, no, sir? Photovoltaics.
Sorry.
Did you take photovoltaic, sir, for input?
No. I have used voltage source over here.
Directly source itself. So can we?
Yeah, voltage source.
Yeah, can we replace with this one with photovoltaics, solar system?
Yeah, you can. You can replace it with the
And
photovoltaic solar system.
okay, sir. One more thing. This after the grid, while make it to if you have to be connected to the load side system, means for example, if you are sending side from your generation side to sending side, transmission side. So if you are using point of common coupling system, there will be point of common coupling system such that there will be one will be the three-phase source, and from the side there will be another one. For example, like wind source or PV sources or such thing. If we use that point of common coupling system, so all these things are be used, or we have to go for any other modulators or anything else?
No, nothing is required. I just
I think
you
what
first
you
go
have to
through this.
do, you need to open the microgrid examples, and there is a one microgrid example is given. Into that one, you will find certain distributed energy resources like PV, wind, diesel. Everything is connected with the grid, and there is a one power PCC is designed, and PCC is there. Okay, so you can get the idea, and you can analyze the stability and other things related to means when we are integrating our DRs with the grid, you can get the idea about all the things, and you can measure the things at PCC as well as load side as well as source side. Okay.
Yeah. Okay. One more.
If you want, the examples are given. You just go through that, and I think you need to explore the software also. Fine. By exploring yourself, you will get a lot of ideas. Okay. And you can opt the examples related to your field and open those examples. Try to run that in those examples, because we have today demonstrated that how you can open one example and you can run. Okay. So open the examples related to your areas and run them, and check how they are modeled. And the purpose of this training is that making you people are aware that how you can work with this tool. Okay. And the rest the technological things like you want to use this particular tool in your field, so we are having a lot of examples. You just go through with them, and we will in coming days we will also demonstrate that how you can utilize this tool in your particular areas. Okay. So
Actually,
it's up to you how. Yes, please.
Yeah, actually, it was first time I have been to this HLL, so that's what the reason I'm being exploring to ask every doubt. Whereas in MATLAB and all things, we are being so far similar.
I
And
appreciate what you are asking, but the better thing, better understanding what I am telling you, please explore this tool.
Yeah.
This is open
Okay.
source, download, install, and explore. And as
Yeah,
much you
sure.
are going to explore, you will get a lot of information, and then you will come up with some really required queries.
Okay, sure.
Okay,
So here is an
because
example for microdynamics. Okay.
being a research person, we need to explore the thing first.
Yeah, okay, sure. Thank you.
Yeah, please.
Any other queries from anyone?
So this is the example about what I am talking. You can see here a lot of DRs are connected, and there is a one PCC is also designed, means a point of common coupling is designed. You can get the idea, and the controllers and other things are there. So you can take this example as a reference. Don't make any changes into this example. Keep this example for you as a reference, and try to copy. If you want to make any changes, copy this example into new file and then make changes. Okay.
Yeah,
so that if in future, if you find any kind of error, you can compare with this one, and you can easily find that where you are getting the problem.
Sure. Thank you.
Okay, so any other queries from anyone? I think. Okay, so thank you everyone for attending the session. So tomorrow we'll meet again at the same time, and from 10 o'clock, and we'll start our session with the new topics. And already we'll also share our videos, YouTube link, as well as GoToWebinar meeting link. Okay, so I think everyone has got the forms for providing their feedback. Okay, so thank you everyone. Thank you for attending the session.
Sir, are you providing this on email or WhatsApp group, the information? Because I'm not getting emails.
I think the information have been provided in the WhatsApp group itself.
Oh, like how can we join that group, sir?
Actually, I think you, if you have registered for this program, you will get the link for WhatsApp, and also the training
I've
video
registered.
link.
Okay, it's there. Okay, in the email it is there. Okay, sir.
Yeah, in the email it is there. So you just need to go through that, and you can join the WhatsApp group. Okay.
Okay, sir. Thank you so much.
Definitely, thank you. So thank you everyone. Thank you once again. I will stop the session over here.